What's the solubility of calcium carbonate in a solution that is 1 molar in sodium carbonate? KSP is 5.0 times 10 to the negative 9. So what's our reaction here? Dissolving calcium carbonate solid, KSP. So what's the product here? Calcium ions in aqueous solution plus carbonate ions in aqueous solution. Initial concentration. Since we're talking about solubility, we're going to assume that we have enough solid to dissolve. Okay, so we're just going to have excess amounts of calcium carbonate. None of this and none of that. What would be our changes? The solubility is x moles per liter, so minus x moles per liter of solution. So you're going to get plus x and plus x. Okay, at equilibrium, what will we have? You still want, if you want to be able to calculate the solubility, you want to make sure you still have an excess of the solid, right? And so you have x moles per liter of calcium and x moles per liter of carbonate. Oops, I forgot something. This is 1 molar in sodium carbonate. So what's my initial carbonate concentration? It's not going to be 0. What is it? 1.0, right? Your sodium carbonate is going to fully ionize into sodium ions and carbonate ions. So my initial concentration is 1 for carbonate. So I have some other source of carbonate. So Le Chatelier's principle tells you what? How is this equilibrium affected by putting an extraneous source of carbonate? Shifts which way? To the left. Okay, so you would expect this to be not quite as soluble. Your X would be not quite as much as what you would expect if there wasn't any other source of carbonate. Okay, so our final equilibrium concentration here is 1.0 plus X for carbonate, right? So this is going to be 1.0 plus X. So let's solve for X. What do we get? X times 1.0 plus X, that's your calcium ions, and this is your carbonate ion concentration, is equal to KSP, which is 5.0 times 10 to the negative 9. This is your KSP. Okay? And to avoid confusion, let me get rid of that X there. So 5.0 times 10 to the negative 9. That way I don't have to worry about that X and that times symbol being confused. Okay? How do I solve for X here? Do you think, okay, right here you have a quadratic equation, right? So this is where you try to look for a time saver. Do you think I can neglect this X compared to 1? Look at this KEQ. Very small number, right? So this reaction will hardly go forward. I don't expect that X to make a difference to the total carbonate concentration. So I'm going to make that assumption that X is very small compared to 1. So how would I simplify this equation? X times 1.0 equals 5.0 times 10 to the negative 9, right? How do I solve for X then? This makes it very easy. X equals 5.0 times 10 to the negative 9. Is that very small compared to 0.1? Compared to 1? What is 1 plus 0.000000000? That's 8. And then 9. 5. That's still 1, right? So I can ignore that X right there. What do you notice about your solubility? It's a very small number, right? Now, you might get a bigger one if there wasn't that 1 right there. What would you get if the 1 wasn't there? Did we calculate the solubility earlier? We did not. Okay, so let's calculate it without the carbonate. without the sodium carbonate. What would it have been if you didn't have sodium carbonate? You would have said x squared equals 5.0 times 10 to the negative 9, right? And then you would have said x would be the square root of that. 5 times 10 to the negative 9 square root. Where's the square root? Second root is 7 times 10 to the negative 5. Okay, this is much smaller. This is without sodium carbonate. And this one over here is with the sodium carbonate. The solubility decreases. This is known as the common ion effect, which is really nothing more than just Le Chatelier's principle in action. Okay? By putting this common ion, you're lowering the solubility of your calcium carbonate because the reaction is shifted to the left. So you're suppressing the dissolution of calcium carbonate. So this is known as this is an example of what we call the common ion effect. Now, like I said, we're assuming here that okay, we're not taking into account here the possibility of carbonate hydrolyzing. Okay, so this is reality is not quite as simple as this, but we're just going to make things simple. We're just going to do it this way. Okay.